John represents Q Magnetics, and he's going to talk about new direction for Benchtop NMR from Q Magnetics.
Hello. Thank you all for this meeting. It's really super interesting. Thanks, Chris, for all the organizing work that you did. So Q Magnetics is, I guess, the newcomer. The design I'm going to talk about is probably the most recent one. And it's different from all the others. And so I'm going to sort of rely on the possibility that you all have some curiosity about what's inside the box and tell you a bit about what this thing really is. That fits me. I'm the physicist and the designer. I'm not the chemist. So this isn't an applications talk, although I'll show you some spectra. So it's 125 megahertz Larmor frequency. We think it's the highest field benchtop, well, the highest field permanent magnet NMR spectrometer, period. In other words, including developments in labs. Maybe someone can correct me, but that's what we think is true. Maybe it's the highest field high resolution NMR spectrometer that's not a supercon. I'm not sure. Might be. So, and if you look at it, you'll see there's another odd feature, which is that there isn't any hole in the top to put an NMR tube. It has two front panel fluid connections, and there's a little sketch on the front panel that shows a black line going through the pole tips of the magnet. So there's a fluoropolymer tube inside that goes from one front panel fitting to the other one and goes through the magnet. So that's another different feature, and I want to spend some time trying to explain why we did that. So we all can feel proud of our permanent magnet gadgets. They were there at the beginning. In 1956 at Stanford, J.T. Arnold built a permanent magnet, and it was the very first time that multiplets were resolved in NMR. So it's really the beginning of NMR spectroscopy. And why? Well, it's difficult to make a stable electromagnet. That's a very challenging electronics problem. People put a huge amount of work into it in the 50s and 60s, but in the beginning it wasn't there. And it was just simpler to make a permanent magnet. So this thing has, let's see, do I have a pointer? You can see that, right? No, you can't see it? Okay, never mind. It has bars made out of alnico, and there's a little trolley arrangement so you can change the gap, kind of like on an electromagnet. You can often change the gap. So that'll be important for what I'm going to say later. Obviously, you change the gap to change the field, just like you do in an electromagnet. By 1975, you could buy a 95 megahertz from Varian permanent magnet NMR spectrometer, and by then there were some supercons, and so they were saying this is cheaper. It's also cheaper than the giant electromagnets that were state-of-the-art sort of in the 60s that, used 20 kilowatts of electrical power and might have weighed more than a ton. But this thing in 1975 also weighed a ton. It really did, literally something like 900 kilograms. Okay, and now today we have these much smaller, diverse, they're all rather different, benchtop NMR spectrometers. And besides telling you about our design, I'm going to try to give some sort of picture about the diversity of these things, and maybe, I'm invading a little bit other people's space, but it maybe gives some idea of why, if you have sort of different design goals, you end up with different designs. I like to keep this in mind in the general subject of instrument design. So the thing on the left, probably everybody here has used. It's the standard 1-inch micrometer. The guts of it are the same as one that would have been sold 100 years ago. And the one on the right is really cool. It's very fancy. It has all kinds of features that the one on the left doesn't have. It's a 2-inch micrometer. There's a lever so you can retract the anvil on the left and make differential measurements. You can even operate it at constant anvil pressure, and you can adjust that pressure. So it has a lot of features. You notice that it costs a lot more. And both of these things are good things. They both have their purposes. If you're making gauge block stacks, you want that bench micrometer. It's great. Okay, but which one, is more common? Which one's sold more? Well, Probably there are 10,000 of the 1-inch micrometers sold for every one of those bench micrometers. And I bet lots of people here have never even seen a bench micrometer like that. Okay, well, so I don't suggest that that's the deal for Benchtop NMR, but at least as background, it means that when you think about design of instruments, it's not unreasonable to think about a simple thing that just does one thing well and might be less expensive, maybe more portable than a thing that does a lot of things. They both have a place. So, okay, so what happened over this 68 years? Well, part of what happened, obviously, is modern electronics. And all these benchtop machines make super heavy use of electronics. They have low noise analog RF electronics in them. They probably all of them have low noise analog, low frequency electronics. They have several embedded processors. They probably all have FPGAs in them. So they have hardware description language code in them, as well as the embedded processor code. And then they all rely on ordinary computers to, collect and analyze the data. So obviously one thing that happened is the electronics revolution. But there's also this question of materials. And to make a permanent magnet, typically you want to have both hard and soft ferromagnets. So a hard ferromagnet, that's a ferromagnetic material that stays magnetized no matter what. It doesn't have to have a field applied to it to stay magnetized. Soft ferromagnetic material is one that is not magnetized when the field goes away. So the hard ones are like the batteries that push the flux around the circuit. And the soft ones are, one role they play is like the wires. They're the flux return. Also, they're used for pole tips. Okay, but what's happened with those? Well, the early ones that you see here were all based on Alnico hard material. But in the early 80s, there was a revolution, and neodymium iron boron was discovered and some other rare earth ceramic ferromagnets, and everything changed. But the interesting thing is, it's not that those have higher magnetization than Alnico. It's that they have higher coercive field. In other words, they're better able to stay magnetized even when the B field that's applied to them isn't favorable. It's maybe in the wrong direction or the wrong strength. So there was a revolution in hard ferromagnetics, and what that did is it made it possible to build magnetic structures that were way, way more compact, lower mass. And these things, everybody here in this room probably has several neodymium iron boron magnets on their body or in their pockets, right? They're just everywhere now. And so we've taken advantage of that. But what about soft materials? This is kind of more strange. So, in the 19th century and before, you could make magnets out of iron. And iron is still a really important soft magnetic material. We use it for flux return. The only other thing that happened was in 1928, long before this period, Permendor was invented. So that's 50% iron, 50% cobalt. It's the highest saturation, magnetization, useful technical material that we have, okay? So in other words, you put it in a strong magnetic field, increase the field until the stuff is magnetized as much as it can be. That amount of magnetization is what you get from Permendor, and it's higher than iron, and it's higher than anything else. And during this whole time of the development of permanent magnets for NMR, that hasn't changed, okay? So this development has not got anything to do with the invention of new soft ferromagnetic materials. Roughly speaking, that's something that just never happens, okay? If it happened tomorrow, it would be a big deal. It would change what you can make, but it doesn't ever happen. So here's a plot of record high fields over time. It's my attempt. I'm sure it's not complete. The green thing are those giant floor standing electromagnets that weigh a ton. So they went from 30 megahertz and topped out around 60, or around 90 rather. And the blue is the electromagnets. So a curious thing is that the electromagnets saturated at a field that's the same as the permanent magnets. You might not expect that because the sort of the battery that's pushing flux around the magnetic circuit is completely different in those two cases. But it's the pole material that determines how high of a field. So what happens is there was a revolution in the 80s in hard ferromagnets. Things got more compact, but it didn't much change the field you could get. The field is due to the soft material, the pole. It's the saturation of Permendor, this iron cobalt ally, that determines the highest field that you can get. Okay, and then the red curve is kind of what we're here to talk about. Those are the recent benchtop NMR machines. And just now with our little thing, we've kind of made a little step above this 100 or 90 megahertz saturation place. But we're still stuck with the same materials. I mean, we're still dealing with permanent pole tips. And so if you ask me, you know, is Q Magnetics going to introduce the QM 250 next year, you know? Well, probably we will, but it will be April 1st. And you should realize that, yeah, it's probably not something real. Probably they're going to saturate right around here, somewhere around here. So I try to give some kind of impression of the diversity of these designs. So these are like analog sliders, you know, design your own benchtop machine. And there, I won't go through them, but you see there's a huge range of parameters. These are, I think, the ones at the boundaries are ones that actually have existed. Besides the analog parameters, there are some sort of ones that are choices. You know, temperature, sample temperature control hasn't been mentioned here, I don't think, but that's an important one. The easiest thing to do, you have to temperature stabilize the magnet. It has a big tempco. You have to stabilize it. So the simplest thing to do is to heat sink the sample to the magnet, right? You could maybe say the magnet's temperature is not allowed to change because that'll change shim in some way. You could say, no, you can change the magnet. Maybe you have to do some reshimming, but you can change it. But a design like that, you're probably not going to be doing temperature sweeps. That's going to be way too tedious. On the other hand, you could say, no, I want it to be like a high field machine. I want to have isolation between the sample and the magnet. That'll take up space between the pole tips, right, if you do that, but you could do that. You can decide how many coils you want. Coils take up space too, right? And that gives you different nuclei and other things. Maybe you want gradient coils. Maybe you think the size of the sample itself is something you can trade, right? Bigger samples take up more space. You could do bigger or smaller. Okay, so let's just leave that there. Those are all choices. The tricky thing, though, is that these sliders are by no means independent, not even roughly. So if you choose to go to very high field, that's going to have consequences in what you can do in this design. And to get some understanding of that coupling, let's look at a sort of archetypal, very simple magnet design, the one on the left, particularly the spherical Halbach magnet. So that thing is just a sphere of ideally perfectly hard, in other words, fixed magnetization, hard magnetic material with a spherical cavity at the center and a funny distribution of the direction of magnetization. Down at the South Pole, it's down in this drawing, and then it's up at the equator, and then it's down again at the South Pole. So it rotates by 360 degrees when you go from the South Pole to the North Pole. So if you do that, Halbach showed that it means that that spherical cavity will have a uniform field in it. And there's a very simple little compact formula for the value of that field. And we can learn some things from it. So the first thing to notice is that there's a log in it. Well, that's really too bad, right? Because that means that the field only increases extremely slowly if you say increase the outer radius, right? Or you could turn that around and say that if I decide I want an inner cavity of a certain size and I want a high field, the mass of this thing increases exponentially with the field I want, right? Yikes. So yeah, that's a terrifying scaling law that you have to live with. But another thing to notice, which is very important, is that the field is scale independent. If I increase all linear dimensions by double them, say, by the same factor, the value of the field, the strength of the field in there doesn't change at all. So that's important. In fact, every permanent magnet design that we're discussing here, doesn't matter where the magnetization comes from, soft materials, hard materials, nonlinear materials, whatever. If you scale them up, just literally change every dimension, the field doesn't change. Okay, that's a sort of a useful underlying law that makes it easier to think about these things. So there are a couple of reasons why one might not want to make a Halbach magnet, although rather shockingly, someone showed a picture of one, so maybe the Magritech people don't agree. I don't know. But so one thing is, if I go and replace a little bit of the magnetic material close to the inner radius, not with neodymium iron boron, but I replace it with permanent, with a soft material, But the thing about permanent is it has a higher saturation magnetization than neodymium iron boron has as a remnant magnetization. So if I do that, if I stick, like right above the North Pole at that inner radius, I put a little bit of permanent in there, the field will go up. It won't go down, even though I've removed hard material. So that's an argument that says that one often would like to have pole tips of some kind, not just make the whole thing out of hard material. The other thing is that the homogeneity of hard material is really awful. We're trying to make part per billion, right, homogeneous magnetic fields here. It's NMR. But if I buy a piece of neodymium iron boron and then I buy another one and another one, the magnetations will differ by like 1%, and the directions will differ. So it's a sort of awful material from the point of view of building something precision. The soft materials are better. Okay, so those are things to keep in mind. And it does, all these magnets have the hard material in them, and it means that there's a really big challenge to produce the homogeneous material, homogeneous field. You can't do it just by sort of buying homogeneous parts and putting them together. So they all deal with that and in somewhat different ways. So this is the design that we have in cartoon form. The green is hard magnetic materials. It's axisymmetric, so it has both a disk magnet that's axially magnetized and ring magnets that are radially magnetized. And then the blue stuff are soft materials. So one thing we do to get homogeneity is we move the hard material away, right, and have the soft material close to the samples. That helps. Another thing we do is there is some mechanical shimming, and I bet all these designs have some mechanical shimming during manufacturing. They may differ a lot in how much. This one, the center section, which has the two pole tips and the central flux return, is a rigid assembly. We don't adjust the relative position of the pole tips at all. But there are shims that can sort of tilt the top part with the disk magnet and the radially magnetized magnet relative to the center section, and likewise the bottom part. So we make a one-time mechanical adjustment with literal shims, mechanical shims, during assembly. It's only a few degrees of freedom, and it's pretty easy to do. And that is a way to get X, Y, Z, and the Z squared aberrations relatively small to begin with. The rest is done as usual with electronic shimming. Okay, but this doesn't tell you about how to get a high field. So here's a thought experiment. Let's say you decide what you want to put between the pole tips. How big is your sample? How many RF coils? How many shim coils do you need? Do you want gradient coils? Do you want thermal isolation, right? You have to make all those choices, and you decide what you want to put between the pole tips, and you get some pole tip gap. And then you build a magnet around it, and then you say, the field isn't as high as I want it, because it never is, right? So then what you do is you could imagine decreasing the pole gap, just like could be done in that 1958 permanent magnet at the beginning. Just decrease the pole gap, only the pole gap, not everything else, okay? So you're not scaling all dimensions, just decreasing the pole gap. And like in an electromagnet, the field will go up when you do that. If the system is not saturated, if you're well below 80 megahertz, and you have a nice parallel plate thing, like a parallel plate capacitor, the field will go up like 1 over the pole gap. Okay, so that'll be good. On the other hand, that 80 megahertz is probably not what you want. If you want higher fields, the field will go up slower. So I've sort of sketched how it goes. The higher you try to go, just lost it, saturate, the slower the field rises. Okay, so that's good. Now you've got your field, but you just crushed all the stuff that you decided you wanted to put in the pole gap. So now you can use this scaling thing, right? And just scale all dimensions up. Now the field won't change, but you'll get your space back. Okay, so that's a way of thinking about designing these things. But it has some bad consequences. It tells us that for fixed that thing is going to go up like the pole gap cubed. That's bad. It'll get massive very fast. But it also tells you that once you decide what your pole gap is, the mass of the thing is going to go up. Well, if you're trying to go above 80 megahertz, it's going to go faster than B cubed, right? So very fast, similar to the Hallbach thing where it went up exponentially. So these are facts that we don't know how to do anything about. And the prefactors to these scaling laws are just material properties, and we're all stuck with the same materials, and new ones almost never appear. Okay, so That's just how it is. Okay, so what did Q Magnetics do? Well, we said we're going to make the 1-inch micrometer. Okay, we're not going to make the bench micrometer, and we're going to make something that just does one thing as well as we can. We're just going to make proton spectra. That's it. Okay, we can do fluorine too. Well, we could probably make a phosphorus, but let's just say we're just going to do proton spectra. And that means we're not going to put gradient coils in there. We're not going to put a bunch of other RF coils. We're not going to put thermal isolation in there either. So we can have the smallest pole gap we can. And then we're going to even let the pole gap be somewhat smaller until we have a field that's bigger than everybody else, because that's what we want to have. And that way, people who just want to make proton spectra might say this is the thing for them, right? So we pick a 5-millimeter pole gap. You can get 125 megahertz Larmor frequency. The sample is going to be in a 1-millimeter ID fluorocarbon tube. It's a flexible tube running from one front panel fitting to the other. There's a guide tube, by the way, down the center of the magnet, and it's straight. And there's doors on the side. So you take those doors off, you can look in from the side and look right through the magnet. So actually, we're not completely wedded to this sample delivery by flow thing. If you put the unit on its side and you want to put a little tiny tube in there, that's fine. You can do that too. So it's sort of adaptable in that way, but mostly we think of it as getting the sample in there by flow. And then you end up, with some performance. We have a line shape that is competitive. The SNR is going to be somewhat lower than a tube machine that has a 5-millimeter ID tube, right? But good for a lot of applications. The magnet weighs about 13 kilograms. The whole thing is 28 kilograms, which is small amongst the competition in this game. Okay, so let me say a couple of words here towards the end about sample delivery by flow. So for walk-up use, you can just use syringes. Imagine you're teaching in a classroom, 20 people, and they all have little beakers, and you want to put samples in. Just take, less than $1 disposable syringe, draw the liquid, squirt it in the machine. That works well. You don't have any more tubes to clean or to pay for or anything like that. And you only really need a few of these. If you have a solvent bottle, you can flush them and wash them, and it's convenient. It's ready to go for hyphenation. I'm showing it here with a little tiny auto sampler. We have also delivered an example where there's a trigger interface to Agilent HPLC. There are some other things. When you sample by flow, the shim won't change, right? Or at least if the susceptibility of the sample hasn't changed very much, it won't change because the geometry is strictly fixed. So that works well for that classroom situation too, where people are just squirting samples in. They're probably all in the same solvent. There will be no shim change. So the shim is very stable when you do things this way. Also, the sample tube is more inert than a glass tube. It's a fluorocarbon, and you can quickly change it. So if you're doing something like reaction monitoring and things go wrong and the whole sample path gets blocked or gets clogged or whatever, and if you've ever had a high field flow probe, it can be troublesome. Here, you take the doors off the side of the machine, you disconnect the little tube, you slip it out, you slip another one in, and you're ready to go. So it's very easy to change the flow path. The sample volume is small. The active volume is really only about 2 microliters. If you use syringe pumps and care and so forth, you can position about 5 microliters of liquid in there. You can use droplet isolation methods if you want. And we can get the same exact spectra that I'll show you in a moment, and maybe you've seen them on our website, with 5 microliters as you do with a more normal, 300-400 microliter sample in NMR. The flow path is also horizontal. That means, in realistic situations, the sample is not perfect. There may be some particles in it. There may even be bubbles, and they may be buoyant or they may sink. Well, they get where they're going a lot quicker in a small diameter horizontal tube than they do in a long vertical tube where they're going to be moving more or less forever, right? So that can be a nice thing too. We have an electronic shim system, just like anybody does, and I'll pass that up. And there's temperature stabilization. You always have to have that in these systems. The magnet is stable enough so that there's no broadening of single shots. To get stability for averaging of many shots, what we do is we do full spectrum cross correlation. So spectrum comes in, and then you want to average another one, which might have been collected 20 seconds later. There is enough drift that you can't just co-add them. But if you cross-correlate them and you translate the second one, you can make it fall exactly on the first one. And as long as there are some high SNR lines in the spectrum anywhere, this works really well. And you can average all night long, and there's no broadening that you get from that. Basically, all the spectra we show are taken that way. It happens in real time, and it's more or less invisible to the user. So here's an example of a reaction monitoring of Diels-Alder reaction, just done in a non-deuterated solvent. And I'll just flip through a couple of others here, and then I'll stop. So there's a spectrum of nicotinamide. It's very high resolution. You can see the difference between the sharpness of the fine structure of the protons that are adjacent to the nitrogen and the ones that aren't. In the bottom spectrum, it's in DMSO, and you can see the broad protons that are directly attached to the nitrogen. This is just something I stumbled across in our hardware store, and it's just squirted in neat. So our shimming and our stability have nothing to do with deuterium. And we have enough dynamic range that you can put pure water in there, or you can put a dilute sample in deuterated solvent in there, and you don't have to change anything. The shimming works the same, and the data acquisition works the same. There is no RF attenuation adjustments in the system because it has enough dynamic range, so you don't need to worry about that. So this one, you squirt it in there, and you can see all of the composition of it. It's some acrylic cement. Okay, and this is our control program that we use to collect data. It has enough features you can reference and fade, so forth. It has enough features that in some applications, like say classroom ones, you don't have to take the JCamp files and open them up in MNOTE, but you could just get direct from there. Okay, so that's what's going on inside the box in our NMR spectrometer.
Questions?
Yeah, please. Oh,
Can you speak to the stray field with
yeah,
magnet design?
it's less than 5 Gauss outside the box. I showed you that picture of the magnet, which has got iron flux return. There's actually an additional shield around it, and it's less than 5 Gauss outside the box. Yeah. Yes, please.
Here, yeah, the box. Yeah.
Sorry?
How long have you been making that box?
We've been shipping for a little over a year. Yeah, shipping a little over a year. There was a 3-year period before that when we were like secret and just doing R&D, and then, yeah. Yes, please.
It seems also that a dedicated carbon magnet would be useful. You mentioned going down to phosphorus, so that just a little bit lower in gamma. What would be the modifications to do there?
Yeah, I mean, but it's that abundance that makes it hard, right? So the sensitivity is just drastically lower. It's definitely possible to do that. Who knows what we'll think we want to do tomorrow. But anyway, today, this is what we did.
More questions? Okay, well, thank you.
Yeah.